In this lecture, we're going to talk about how to implement the Fourier transform over the integers modulo n as a quantum circuit. Okay, so let's first talk about the classical case. So we're going to assume that n is a power of 2 here. And what's our problem? So we're given some vector v, and we want to output the Fourier transform of v, fn times v. Okay. So classically, just normal matrix vector multiplication takes time order n squared. And that's basically the number of entries of the matrix. And we're going to have to iterate over all the entries of the matrix in order to figure out a matrix vector product. Now, when Fn is, in the special case of Fn, the Fourier transform, there's actually a classical algorithm that can compute this matrix vector product just in time order n log n. Okay, and that's quite a remarkable result and has lots of practical applications. And I encourage you to go ahead and look at how the classical fast Fourier transform works. And so note that this order n log n, this is nearly optimal, right? Because it's always going to take you time omega n just to write down the output, because the output has that many entries. It has n, capital N, many entries. Okay? Okay, so, but in this lecture, we're going to talk about the quantum case, and we're going to design an efficient quantum circuit that outputs Fn. So given as input a quantum state V, it outputs Fn times V as a quantum state. Okay, and that's the important caveat here. So we're not going to explicitly output all the entries of Fn times V. So you're not going to like have this vector written down on a piece of paper at the end of the day. But you're going to have a quantum state that encodes Fn times V. Okay, so you can continue to use the output of this quantum state in the rest of your algorithm. Okay, so with that caveat, right? So that caveat basically allows the potential for us to get sublinear running time, right? Because we no longer have to explicitly write down all the entries of the vector. Okay, and indeed, we're going to be able to output this Fn times V as a quantum state by a circuit that only has log squared n many 1 and 2 qubit gates. Okay. So as I said in lecture 1, we're not going to restrict the gate set that we use for this presentation, because now we already know that whatever gates we use here can be efficiently simulated by your favorite universal gate set. Okay, so now let's start to get into the details of how we can implement the Fourier transform as a quantum circuit. So remember that we assume that capital N is a power of 2. So we're going to represent elements of Zn by their corresponding binary representation. Okay, and I'm going to go back and forth, thinking of A both as an element of Zn and as an n-bit binary string. Okay. Okay, so it suffices for us to design a circuit that correctly works on basis vectors. Okay, so if we can show that the circuit has the right behavior on ket x for every n-bit binary string x, then it's by linearity, we know that it's going to have the right behavior on any vector. Okay, so let's just recall what the Fourier transform of ket x is for a basis state x here. So Fn times x, well, this is just going to select the xth column of Fn, okay? And the xth column of Fn is exactly this state here. So if you remember, the rows of Fn are the chi-a star vectors. Okay, so if we look at a particular column, then this is what it's going to be. And we know that chi-a of x star is equal to omega to the minus ax, where omega is e to the 2 pi I over n is our primitive nth root of unity. Okay. All right. So we want a circuit that for every basis state x transforms x to this state here. Okay. Okay. So let's just look at an example to kind of get our bearings here. Okay, so let's say we're looking at 4-bit strings, so little n is 4, capital N is 16. Again, this is the behavior that we want. Okay, so if I just write that out here, so 1 over root n, that's 1/4, and we want to map x to this so the coefficient of the all zero state should just be 0. The coefficient of the state here encoding 1 should be omega to the minus x. Here, this is the binary representation of 2, so we want the coefficient to be omega to the minus 2x, etc. Okay. Now, we can notice an amazing thing here. This state that we want to create, it's actually a product state. Okay, so you can actually write the state as the following tensor product. Okay. So maybe let's just see why that's the case. Okay, so let's say when a is equal to, say, 9, okay, so it has the binary representation 1, 0, 0, 1. Okay, and now let's look at what coefficient we want in front of this state, right? So so here we see, of course, we want omega to the minus 9x as our amplitude on this state. Okay, and let's see why we actually get that in this tensor product here. Okay, so in this tensor product, what is going to lead to the state labeled by 1, 0, 0, 1? So we're going to take this term here, then we take a 0 term, another 0 term, and this term. Okay, and so then we get 1, 0, 0, 1. Okay, now what is the coefficient in front of that? Well, it's omega to the minus 8x. Here we just pick up a phase of 1. Again, we pick up a phase of 1. And here we pick up a phase of minus x. So times omega to the minus x. Okay, that's 1, 0, 0, 1. Okay, so we get exactly the coefficient that we want in front of this state. Okay, and you can kind of see what's happening here. So when the corresponding bit of a is 0, then we're not going to pick up any phase. When a bit of a is 1, if the ith bit of a is 1, we're going to pick up a phase of omega to the minus 2 to the I times x. Okay, and when we sum up those terms of omega to the minus 2 to the I times x, for all I, where ai is 1, and we multiply those together, take the product of all those terms, I should say, then we're going to exactly get omega to the minus a times x. Okay. So I think we have that written out on this slide. So the general case works in the same way. We have this tensor product here, and that is exactly equal to the state that we want here. Okay, and again, the way that you can prove that is just term by term. So what is the coefficient of this state here, of a general state? Well, in this term, the coefficient is just omega to the minus a times x, times 1 over square root of n. And in this tensor product, the coefficient of this is, well, we again have 1 over square root of n, capital N here. And then, well, what coefficient are we going to get? Well, for every bit where aj is 0, we're just going to pick up a phase of 1, so those don't really matter. And whenever aj is 1, um, then we're going to pick up a phase of omega to the minus 2 to the j times x. Okay, and again, we take the product of that over all j's where aj is 1, and that's just going to be omega to the minus x times the sum over j, aj 2 to the j, and this here is exactly a. Okay, so we get omega to the minus ax, just as we wanted. Okay, so that's the kind of that's the first important fact, that the state that we want is actually just a tensor product. Okay. Okay, so what's the good thing about that? Well, if the state that we want is a tensor product, then we can kind of just focus on creating each individual term here. And if we can create each individual term here, well, then it's easy just to tensor product them together. Okay, so now let's just focus on creating the state in one of these individual terms. Okay, so I'm going to call these terms zk. Okay, so zk is going to be the term of this form, okay, where we have 1 over square root of 2 times ket 0 plus omega to the minus 2 to the k times x times ket 1. Okay, so so this tensor product here is just a tensor product of the zk's where k ranges from 0, so this would be z0 here, and this term here is z in minus 1. Okay. All right, so now we're just going to focus on creating one of these zk terms. So let's dig into this term a little bit more. And for the previous step, we kind of looked at the binary expansion of a. Now we're going to look at the binary expansion of x, and we're going to use that. Okay, so omega to the minus 2 to the k times x, that's of course equal to omega to the minus 2 to the k times sum over j, xj 2 to the j. This is just, again, using the binary representation of x here. And now I can just absorb this factor of 2 to the k inside here. So this is a product from j is 0 to n minus 1, omega to the minus xj times 2 to the power k plus j. Okay, good. Okay, so right, so from the previous slide, we have a product from j is 0 to n minus 1, omega to the minus xj times 2 to the power k plus j. Now let's just remember again what omega is. That's going to help us simplify this term. So omega is e to the minus 2 pi I over 2 to the n. So I just plug that in to the expression from the last slide. Okay, and now notice what happens here. Okay, so when 2 to the k plus j, so I should say rather when k plus j, let me just say when k plus j is bigger than or equal to n, right? Then this term 2 to the k plus j over 2 to the n. So when k plus j, let's take it a special case. Let's say that k plus j is actually equal to n. Okay, so then this is 2 to the n over 2 to the n. So that's just 1. Okay, so that simplifies to be 1. So then we just have e to the minus 2 pi I times xj. Okay, but that's always 1, right? Independent of what xj is. And a similar thing is going to hold whenever k plus j is bigger than n, right? When k plus j is bigger than or equal to n, then this term is going to be an integer. So here we're just going to have an integer multiple of e to the minus 2 pi I times xj. And that's always going to be 1. Okay, so they're not going to affect this product. Okay, so what that means is that we can restrict this product just over the range where j is 0 to n minus k minus 1. Okay, because these terms where k plus j is bigger than or equal to n, so in other words, where j is bigger than or equal to n minus k, those terms are just 1, so they don't contribute to the product. Okay, so this is kind of the second very important observation for implementing the Fourier transform as a quantum circuit, is that zk only depends on the n minus k least significant bits of x. Okay? Right, so this phase that we want to create on ket 1 here in zk, it only depends on the n minus k minus 1, n minus k least significant bits of x. Okay, so it depends on x0, x1, up to xn minus k minus 1. Okay, so that's going to be the second very important fact that we use to create this quantum circuit. Okay, good. Okay, so yeah, so now we basically have everything we need to actually build the circuit. But to understand how this works, let's go ahead and start with the easiest case, okay, and that is looking at zn minus 1. Okay, so from what we said on the last slide, zn minus 1, it only depends on the least significant bit of x. So it only depends on x0. Okay. So let's go ahead and see what happens here when we plug in n minus 1. Okay, so n minus 1, when k is n minus 1, so indeed this becomes 0 up here. So we're just looking at one term in this product where j equals 0. So this is just omega to the minus x0 times n minus 1 plus 0, so 2 to the n minus 1. Okay? Okay, good. So that's what we have written here. Okay. So remember again, what is omega? It's e to the 2 pi I divided by 2 to the n. So this 2 to the n minus 1, so we can simplify this because the 2 to the n minus 1 divided by the 2 to the n is just a factor of a half. That cancels the 2 and the 2 pi I. Okay, so this is just e to the minus x naught pi I. Okay, so in other words, this term is going to be 1 if x0 is 0, and it's going to be minus 1 if x0 is 1. Okay, so now this is a very familiar expression, right? This is just the Hadamard applied to x0, right? So if x0 is 0, the Hadamard maps it to 0 plus 1 times 1 over root 2. And if x0 is 1, the Hadamard maps it to 0 minus 1 times 1 over root 2. Okay? Okay, super. So now we know how to create zn minus 1. It's very simple. We just apply the Hadamard to x0. Okay, so yeah, so there's the first part of our circuit. Okay, let's just build up the complexity step by step. Okay, so let's consider the second easiest term. So that's zn minus 2. Okay, so again, if we plug in n minus k equals n minus 2 into our formula, then this state is 1 over root 2 times ket 0 plus minus 1 to the x1 times omega to the minus x0 times 2 to the n minus 2 times 1, ket 1. Okay, so again, zn minus 2, it just depends on the two least significant bits of x. So now it depends on x1, and now it also depends on x0. Okay. And now we see that we can kind of build up the state iteratively, right? Just by multiplying the right phases on the one state. Okay. So if you just ignore this term for a second, right, then it's exactly what we had in the last case, 0 plus minus 1 to the x1 times 1. So we know how to do that. We can just do a Hadamard on x1. Okay, and now, but in reality, we can't just ignore this term, that this term is here. So we need to multiply the phase of the one state by this term as well. And how can we do that? Well, we can just do a conditional rotation. Okay, so depending on the value of x naught, if x naught is 0, then we don't rotate at all, right? Because this is just 1. And if x naught is 1, then we rotate by omega to the minus 2n minus 2. Okay, so this exactly gives us what we want. This creates the state zn minus 2 on this second wire here. Okay. Okay, so now we've seen two special cases. Let's go ahead and try to do the general case. So let's create the state zk. And it really goes in the same iterative way that we saw in the first two cases. Okay, so zk. So as we said, this only depends on the least n minus k significant bits of x, right? So it depends on the bits x0 up through x n minus k minus 1. Okay, and now maybe let's just work out the first couple of terms. So what is the dependence on x n minus k minus 1? So in this formula, when j is n minus k minus 1, so what do we have here? So in that case, we have k plus j. So k plus j is just going to be n minus 1. Okay, so we have omega to the minus xj times 2 to the n minus 1, which is the same as, so we have omega to the minus xj times 2 to the n minus 1, which is the same as, e to the minus I pi xj. Okay, so yeah, again, j is n minus k minus 1 here. So we know how to create that phase on the one state, right? That's just a Hadamard. So our dependence on x n minus k minus 1, we can achieve that just by doing a Hadamard. Okay, and then what's the dependence on xj when j is n minus k minus 2? Okay, so when we plug that in here, we want to multiply by the phase 1 if x n minus k minus 2 is 0, and if x n minus k minus 2 is 1, then we want to multiply by the phase omega to the minus 2 to the n minus 2. So we can do that with this conditional rotation here. Okay, and etc. We just keep applying these conditional rotations. Okay, and notice that we're only modifying this wire, right? These are all just conditional operations here. So at the end of the day, here we still have x0, and here we still have x1, okay, etc. And here we've created zk. Okay, so that's very important for how we're going to globally design the circuit. And how many gates do we use here? Well, we just use one gate for each bit of x from 0 to n minus k minus 1. So that's n minus k gates in total. Okay, so we've used n minus k gates, and we've constructed the state zk here. And building zk here, we didn't have to change the the state on any of these other wires. Okay, so these wires still have the right values of xj. So what we're going to do is we're going to kind of first create the state z0. Okay, so we first create the state z0 on this last wire here. Okay, so z0, it actually depends on all the bits of x, right? But when we created z0, then we didn't mess up x2, x1, or x0. Okay, and now when we go to create z1, well, z1 doesn't depend on x3, right? Because z1 just depends on the n-1 least significant bits of x. So it doesn't depend on the most significant bit. Okay, so the fact that we've changed the phase on this last wire, it doesn't matter for us. Okay, that's fine because we don't need to use it in order to create z1. Okay, so then we basically apply our little circuit block here to create z1. Oops. And again, that didn't change the phase on the wires for x1 or x0. So then we can apply our little block to create z2, and then we apply our block to create z3. Okay. And you see that, you know, this block, circuit block takes 1 gate, then 2 gates, then 3 gates, then 4 gates, right? So just as we said on the last slide, to create zk takes n-k gates. So the total number of gates is just 1 plus 2 plus 3 up to n, which is n plus 1 choose 2. Okay, so the one slight defect with this circuit is that the output bits are in reverse order, right? So instead of having z0 at the top and z3 at the bottom, we have it in reversed. Okay, but we can fix that just by doing n-2 many swap gates. So adding n-2 many swap gates here at the end, then we can put the output bit qubits in the right order. Okay. So overall, here we have a circuit that implements the Fourier transform, and the total number of gates is order n squared. Okay, that's what we promised. Okay, so again, we've used these conditional rotation gates here, but as we saw in the first lecture, you can efficiently approximate this circuit, you know, using you know, whatever other universal gate set that you want to use. So we've used n squared gates here. You can also approximate the Fourier transform to precision epsilon with just n log n plus n log 1 over epsilon many gates. Okay, and you know, here we just design the circuit when n is a power of 2, but you can there are efficient implementations of Fn, approximate implementations of Fn for any powers of n, not just powers of 2. Again, we're going to use that fact later in this course. Okay, so that is all about the implementation of the Fourier transform.